All right, we're back. So, let's take a look here. Let's see, view, selection. There we go. So, as before, we did a constant current, so the B field is constant. And, well, not as before, in a similar fashion. And then we took some voltage data. We changed the voltage, that's our independent variable, and then we measured diameter in centimeters, and we came up with an error. In this case, 0.5 centimeter. I would bet a lot of you use 0.2, and that's fine. So now we have to divide by 2, and I put multiply by 0.01, but if you like, we can divide by 100. So then it's a little more intuitive. 100, excuse me, wait a minute. Not I put multiply by 100. I'm going to divide by 100. All right, because that's right. They're less meters, 10 to the minus 2 here. And just to make it more intuitive. And then you do similar thing. Let's see what it says here. Oh, I got clever here, but it'll just we're dividing by 2 again, and divided by 100. So the plus minus divide by 2 and divide by 100, and we get ourselves our plus minuses. And then, of course, r squared. Now remember, our goal is to plot r squared as a function of voltage. So here, so we took one of the root equation of what is it? F equals mv squared over r, and equals to EVB. That's all in the manual. So I'm gonna not get into that. That's for someplace else. We assume we know what's going on here. So we're going to say that this equals to the radius, and we want to square it. And so we can use the fill handle. Not quite sure why these extras are here for. Now what's the plus minus? Okay, so we have to... here it is. So we have our, oops, let's get that out of the way. Our table, and so we're going to use the top one, F equals AB, and then A will be R, B will be R, and you see that's the fractional error, remember, plus minus A over A, plus minus B over B. It just happens that in this case, since it's r squared, it's the same thing. Remember, resist the temptation to cancel r's. So basically, it's 2 times this plus minus r over r squared. And when we take the square root, and remember the r squared's out front, so instead of just simply being the fractional error here, it's square root of 2 times that fractional error. When you do the constant voltage or current 1 over r, in that case, the error of 1 over r is a little simpler because the term with the 1, f equals a over b. So if a is equal to 1, the plus minus of 1 is 0 because it's a constant. All right, so we get that r squared times square root of 2 times the fractional error of r. That's our plus minus r squared. Okay, so equals the r squared times the SQRT2 and times the plus minus r divided by r, and then there's our plus minus. So now the pro tip here is to make our plot, to make it easier to deal with the error bars. So we're going to pick voltages here, and we hold down the control key and pick the r squareds. Insert, and we want a scatter plot. There they are. And now we want to add error bars. So click on it. And then, of course, we need to go click, so we get the, well, I wanted to get the, there it is, the sidebar. And chart design, we'll make believe we all have max. Well, I think even on a PC, you have to, for chart design, you have to get the, add the error bars, and we'll say standard. And then the graph is still highlighted. Oops, now it's highlighted. And we get these two extra menus. So I want to format and the X error bars. First of all, fixed value of 0. And they disappear. And then we want to do the Y error bars. And that's custom, specify, and let's see if we can find them. Oh, we got lucky. They're right here. Whew. So you may have to, if you can't see them, and it looks like I can't maneuver anything. What if, if I have that there? No, I can't remove. So if you get skunked, then just stop this for a minute and then make sure that they're available. Okay, then format again. I have the graph highlighted. And, you know, partly you can also maximize it. I have this thing squeezed into a small fraction of my screen because you guys are not likely to have as high resolution screen as I do, and I don't want it to look too tiny when you're watching it from your laptops. Plus I have a separate monitor. I'm not even using my laptop screen. Okay, so there's plus minus. For the positive side, then we're just assuming symmetric error bars as usual. And okay. And there's the error bars. Okay, so next, let's see. Let's zoom out on this a little bit. 182%. So let's make it 150%. All right, now we can see a little more. Okay, so we want to, here's our equation. The slope is what's inside of there, here. Right now, a slope is a slope is a slope, so we just simply create the fit equation. And let's see. So it looks like hit this with, well, we'll try 0.1 to start. 0.1, I think it's smaller than that. And 0. Okay, so this equals the slope. And we need our dollar sign, so we can click inside the box. Great. Oops. Dollar, not percent. Times, and that would be the value of the voltage at that point. And I'm just doing this scroll bar on the bottom. And I click in here just to make sure. Plus the y-intercepts, and I need my dollar signs. So, whoops. So I'm off by four orders of magnitude. Nice. So let's put in 3 zeros to start with. And, oh, sorry, I was looking at this one. This is what I care about. Okay. So that one is still too big. So I'll add another 0. Okay, now it's in the ballpark. All right. And if we like, we can do the res equals data minus the fit. And the res squared is simply that squared. And we'll fill that in. And now we gotta do the chi-squared. So instead of assuming you watch the other one, let's see. Okay, so let's just go here. And there's the chi-squared. And we'll bring it back here. Yeah. And we'll paste it as a picture. All right. So once again, the chi-squared is just you recognize this up here, that's the residual squared. And now we divide by the plus minus of each data point. And what that does is that it downplays the data points that have larger error bars. Oops, get downplayed. They contribute less to the sum than the ones with small error bars. Oops, so why it didn't like that. Oh, I forgot to say, okay, it's getting a little screwy. All right. I clicked on the symbol again. All right. Equals the res square. I don't know what's going on here. K 4 minus, no, divided by the plus minus H4. I think now if I let's see if I fix that now. Yep, the changing of the zoom. Fix that. So let's zoom back in again. Let's say 140, give us a little more real estate. Okay, so this, let's do it one more time, equals the res squared divided by, and I may have even made a mistake, so I'm glad I'm doing this over again, the plus minus, and we have to square it. I forgot that part. Okay. And so we fill it. And yeah, so these all have pretty much the same error bar. But as always, think about a point way out of here. And we know that, well, you guys, I guess, haven't done it with paper and pencil. But the idea is to, as always, that you want a line through there that has the distances above and below, the residuals, the sum of them to be about 0. And we use res squared just because the computer can't understand the residuals alone. And the res squared gives us a convenient way to get the best possible fit. And the sum of the chi-squared just simply tells us it downplays the bad data points that have large error bars. But the big deal, though, is that the chi-squared allows us to determine the plus minus on the slope, and I'll get to that in a minute. It's a standard way to get the plus minus on the slope. Okay, so let's add the fit line first here. Select data, add. So the title is fit line, and the x values are the volts. Now we want the fit line to extend from 0 to past the 220 here, so I picked 250 as a convenient number. And then I did forget here, but I think it won't complain. And great. Okay, so I just drag this down. And now there are our points. So we need to turn that into a line. Format, series fit line. And let's see, oh yeah, solid line. And we'll make it a deep red. And make it really thin. And then we want to mark our options, none. Okay. So, this could be a little bit bigger. I don't know if it's doubling it. Doubling is too much. So, 1.5 E minus 5. Whoopsie. Something went wrong. Okay. 1.5 E minus 5. So halfway in between. And it looks like our y-intercept is a little small. But let's let the computer figure it out for us. So we want to get both sums. The other video I made, I went over, I showed you how the sum of the chi-square and the sum of the res square gets you somewhat different results. Equals sum, of the res square, chi-square, excuse me. And these numbers are, at least here, are so small that we need scientific notation here. There we go. And this one could use, Well, we'll stick with that. We need that number of sig figs. We need it in a minute. So we go to data and the solver, and we want to minimize the sum of the chi-squares, and we want to vary the slope and the y-intercept. Uncheck that guy, and we solve. And let's, ooh, look at that. All right, I like that. All right, so now we want to get the plus minus slope. And so, let's see. So let's call this the best fit. And this is and we'll call this one of the extremes. And then, you know what? In the other video, I made a mistake about the plus minus on the. Yeah, I have to fix that. The plus minus on the E over M measurement. Okay. But anyways, I'll do it right here. So we have the sum of the chi-square here. So what we want to do now is, sure, let's make sure we got to go over why we're doing it. So you should recognize this plot of, say, the sum of the residuals squared, and the sum of the chi-square is very similar in that if you plot the parameter like the slope on the x-axis and the value of the sum of the r squared or the chi-square, you're going to get this parabola. And when we use the sum of the chi-square, the official definition is that the extremes of the slope are the value of the slope that creates an increase of the sum by 1. The proof is ridiculously long and complicated, but we don't care about that. It's only if you were a physics major. And who the hell would ever do that, right? Okay, so we've got our best fit here. And so I want to copy, well, I don't think we can copy paste, so into this dialog box for some reason. We have to hand type. So we want a value of, and we see that for some reason it's slightly different this time around, 1.6960. And we only want to change the slope. And so we hit solve. And we got something happen that doesn't seem outrageous. We say OK. And now we take this and we copy it. And we paste the value. And now we need to get back the original. So I want to go to solver again. And all I want to do is change this to minimum. Solve. And there it is. In fact, I am going to hedge my bets here because let's put a paste there because this thing is could change. So I'm going to copy it and put paste value there. And in fact, I should do all three of these. Let's format them to scientific. And I guess 2 is good enough. So the plus minus is equal to the absolute value of the difference between these two. And when we are so close to, we can't, at the end of the day, there's not, but I would tell you that there's a debate about how much of a parabola this is when it's a two-parameter fit, and we're only varying chi-squared by that little amount. We can assume it's a parabola, so that means that, notice that the extreme was less than the actual value. It randomly might give us the high value, but we don't know. I don't know how to force it to give us one or the other. So we just assume it's symmetric. So there's our plus minus. Now again, this is what we plotted, and it's a derivation of the root equation, which is the centripetal force, mv squared over r, and the Lorentz force, which is the charge q, so I just looked at a text. The charge q times the velocity times the magnetic field, EVB, and then we can convert things to I and voltage, current and voltage. This is the constant current. Oh, shit. I'm answering the text and I forgot the recording's running. Sorry. Let me stop it for a minute. I'll see if I can edit this out. All right, I just got a couple texts and I made everybody upset. Oh, I did it again. Holy shit. Okay, well, I'll get it out of there. Oh, goodness gracious. Okay, so we need to calculate the E over M. So we're going to use this. So equals 2 divided by the slope and divided by the value of the magnetic field squared. And there it is. And we square it. And that one didn't turn out to be so good, unfortunately. So we see we have a 19% error, and that's just the difference divided by the average of the two of them. And then we want to do a percent error. And so we need a plus minus of the E over M. So that would be using this one. So this equals, here it is, 2 divided by this A divided by the B squared once again. Here it is. And now we want to put, we'll just copy, paste the number here just so it's consistent with what's up above. And then we can copy this. And this is the plus minus. Oops. Oh, careful. That doesn't seem right. Oh, yeah. It's 2 orders of magnitude smaller. Of course. That's right. That's fine. Okay. All right, so this is plus minus on E over M. And we gotta put an escape character here if we do, which is this diacritical mark. Oh, maybe not. Then is it an apostrophe? Yeah, let's put an apostrophe there. Here it is. There we go. Then plus minus E over M. And then so then the percent error is percent error equals to the plus minus divided by the best fit times 100. And we see we got plus 1.99%. So that is not so bad. But our percent difference is 20%, so that's too bad. Fine enough. I mean, in a sense, we could argue that we've made a new measurement because our 1.99 is smaller than the percent difference. So that means that maybe the previous measurement might be wrong. It's probably not true, but at least we have something to start with here. We might go back and say, hey, we must have some kind of systematic error because we came up with something that is pretty good as far as percent error, but at the same time, the difference of the previous measurement was so big that we can't. We probably did something wrong, and in this case, we would probably go back and do it over again because we'd be like, crap, maybe we can apply for the Nobel Prize, but we might find, oh yeah, we did something wrong. Okay. Time to publish.